Okay, what will you need to know for your Unit 4 exam? So I've got anatomy of the sun, and so I just kind of brought in a figure of the sun. I know it's kind of small, but you want to kind of know the 3 internal layers. Of course, that's the core, the radiative zone, and the convective zone. I think you had a homework question about that. The 3 external layers would be the photosphere, the chromosphere and the corona, okay, and then solar wind. So actually it's all there in that figure, all the words I just said. The flight or the plight of energy as it leaves the core, because of course energy is always created in the center of the core of stars. It kind of has this random walk through the radiation zone, okay, and that takes about 100,000 years. I just think that is so amazing. Then it hits the convection zone, finishes working itself out to the photosphere, and then from the photosphere it gets to the Earth in about 8 minutes. All right, the next one, nuclear fusion in the core of the sun. So I brought in something from our textbook, or from, excuse me, your lecture slides. How do you get what's going on in the center of the sun? Basically, you get 4 protons in. You get 1. Protons are, I'll put next to the protons. Protons are basically the hydrogen atoms. Hydrogen, and you get out a helium nucleus. You get gamma rays, which are your energy, positrons, and neutrinos. And there also, in your lecture notes, I said, basically you lose some mass, and that mass is converted into energy. The next term, gravitational equilibrium. It's a balance between gravity pulling in and the outward pressure from the energies of the sun. That's gravitational equilibrium. Sun's built-in thermostat looks like this. Where basically, if it does cool down, that's in red. If it does cool down, it will contract, and when it contracts, it will heat up, which means it kind of corrects for being cool. Over there in purple, if it heats up, it's going to expand, and it's going to kind of cool down. So that's kind of how, even though it's gravitational equilibrium, it kind of has this a little bit of wiggle room, so it kind of maintains the same temperature. Neutrinos are those subatomic particles that are formed during fusion. Come on. Okay. Neutrinos, they're relatively elusive because they don't interact with matter. They pass right through matter, but they're formed during nuclear fusion. And then sunspot cycle, it's kind of like playing Twister, where basically every 11 years it gets kind of crazy distorted and it kind of resets. And so it's because the sun has differential rotation, it's rotating, so it gets kind of messed up. The sunspot cycle, when the sun is active, actually we get the sunspots, solar flares, coronal holes, coronal mass ejections, filaments, and prominences. And then I brought in this little figure to show you the thing about the magnetic field. The purple is the magnetic field in that case. That's all about the sun. On to stars. Luminosity is a basic measure of the energy output of a sun per second. Its units are watts. We talked about 2 brightness scales. The apparent brightness is a lowercase m, how things appear. And remember, it's affected by distance. So actually, apparent brightness is equal to luminosity divided by 4 pi distance squared. The scale for apparent brightness, the smaller the number, the brighter the object is. The dimmest we can basically see in dark skies with our naked eye is a magnitude +6. Absolute magnitude then corrects for distance. Absolute magnitude is how bright an object would appear if it were placed at the same distance from us, 10 parsecs away. Absolute magnitude relates directly to luminosity. The 7 stellar spectral types are O, B, A, F, G, K, M. O is the hottest one, M is the coolest. Binary stars. Most stars come in pairs. They're gravitationally hanging out. A visual binary, you can see both stars separate. Spectroscopic binary, actually you can see that there are two stars using the Doppler effect and their spectral lines. A pair of stars that are eclipsing is a way to see that you actually have two stars. The Hertzsprung-Russell or HR diagram, we spend a lot of time talking about those and stars. Remember, it's a scatter plot that basically has temperature along the x-axis and luminosity along the y-axis. HR diagrams, kind of, you can divide them up, stars into kind of three groups. One group would be the main sequence, the second group would be the giants, and the third group would be the white dwarfs. Main sequence stars are stars that are fusing hydrogen to form helium in their cores. And here I just kind of have an excerpt. This diagonal line is kind of this diagonal line over here. Basically, that's our main sequence stars. They're high mass and then low mass at the high mass at the upper left-hand corner, low mass at the lower right-hand corner. Then here, with regard to difference between high and low mass stars, color, luminosity, and surface temperature. So I went ahead and underneath those, I put low mass are red, low luminosity and cool. High mass are blue, high luminosity and hot, as they are main sequence stars anyway. We talked about two types of clusters of stars. There are globular clusters. They're old ball of stars located in the halo. And they're open clusters. They're relatively young, spread out, and they're located in the disk of our galaxy. Then the last one, using HR diagrams. If you put a whole cluster of stars on an HR diagram, and for this one, each color represents a different cluster of stars, then actually you have a different turn-off point. Remember that, must have been on here somewhere, that high mass stars live their lives a lot more quickly, so they will peel off of the main sequence before the low mass stars. So you end up with what's called a turn-off point. The turn-off point is where the most massive star left on the main sequence is. And we can tell how old a cluster of stars is that way. Chapter 13 and 14, kind of the lives of stars. Actually, my terms on my review sheet, sometimes, actually 14, I think really should be in chapter 13 as it's on my review sheet, but it all works out. So a molecular cloud is a giant nebula where lots of stars can be born. A protostar is the nubbins of a wannabe star. When a protostar will continue to collapse and only stop collapsing when it becomes a main sequence star. It begins fusion in its core. Main sequence star, or main sequence stage, that is when a star first begins fusing hydrogen into helium in its core. The main sequence stage is the longest stage for all stars. Planetary nebula is actually kind of the shell of material that a relatively low mass star ejects as it's dying. At the center of a planetary nebula is a white dwarf. Why do stars age differently? It's all about mass. The more massive the star, the faster it lives its life. Brown dwarf is a failed star. It's less than 0.08 solar masses. Helium fusion, actually that's the type of fusion that begins after hydrogen fusion, and helium fuses to create carbon. And then on to the last chapter. So we talked about this whole companion thing going on. So you see the red is my live star, my giant companion. WD stands for white dwarf, the retired star. So what can happen is your swollen giant can dump material on your white dwarf, and two things actually can happen from that. So starting with the first one where I have listed here, supernova, basically the white dwarf picks up enough matter to come out of retirement, to begin nuclear fusion in its core, to fuse carbon, and it just blows up because it can't handle that. The massive star supernova, that's actually a type 2 supernova, and that happens when a star that's more massive than usually 8 solar masses ends its life. It fused silicon into iron, and it can't fuse iron into anything else, so it basically blows up. The massive star supernova leaves behind either a neutron star or a black hole. Red giant is kind of the upper moving off the main sequence into the red giant area. That is just significant in that it's run out of hydrogen in its core to fuse. Now it's fusing something else. A white dwarf is a retired star. Only low mass stars, 8 solar masses or less, can give you white dwarfs. Basically what a white dwarf is an orb of carbon. Chandrasekhar limit, that's 1.4 solar masses, and we talked about that in terms of, first, a white dwarf. If a white dwarf exceeds 1.4 solar masses, then basically the normal matter it is with electron degeneracy supporting its mass is not going to work. Accretion disk, we even talked about that just now with a black hole and a companion, but an accretion disk is basically kind of fresh matter being dumped, in this case of stars anyway, being dumped from a companion onto something that's retired, either a white dwarf, a neutron star, or a black hole. And it has a lot of kind of friction, makes it hot. Nova. So nova actually also involve a white dwarf and a bloated companion, but nova, the nuclear fusion occurs with the fresh hydrogen that the white dwarf got from the companion star. So nova actually can reoccur. And the last one here, gravitational redshift. That poor sucker who went into the black hole, but we saw gravitational redshift just with the spacecraft that was in the vicinity of the black hole as well. So gravitational redshift just basically, the gravity is so extreme that the light trying to leave in the vicinity of something that has a lot powerful gravity, like a black hole or a neutron star, that light, some of its energy is stolen, so actually it now appears at a longer wavelength colors than the shorter wavelength colors. Then gravitational redshift continued, that's gravitational redshift. Neutron star basically is neutron soup formed from the immense pressure from a dead star or exploded star, making protons and electrons form into neutrons. Pulsar, we talked about, pulsar is a signature of a neutron star. Like, really? Come back here. Only does what I tell it to do. I get in a hurry, and that's what happens. All right. We did that one too, didn't we? All right. Okay, I'll just leave all this up here. Neutron star, okay, pulsar is a signature of a neutron star, and I brought in kind of at the top there, you can see the neutron star has energy being emitted kind of at an angle from its axis of rotation, and it creates kind of like this lighthouse effect. Formation of a stellar black hole, neutron degeneracy can't support the star, so basically the fabric of space and time collapses in and on itself. That can occur when the corpse that's left is greater than 3 solar masses. The anatomy of a black hole is down here at the bottom. I just put that up just this morning. So we have singularity, the event horizon in purple, and the Schwarzschild radius in orange there. Black hole effects falling into a black hole. So I didn't talk about length, but I talked about how time slows, and I didn't talk about mass either. Time slows, actually length would shorten and mass would increase. So I guess the only one there is time dilation. The last one, stages of a low mass and high mass star. I went ahead for your convenience here in blue. I have how does a low mass star live its life. It starts out as a protostar, then arrives at the main sequence. It goes into a giant stage. It fuses helium into carbon. It'll end up ending its life as a planetary nebula and a white dwarf. High mass stars have very similar, even up to kind of the giant or red giant stage. They end up fusing heavier elements into, ultimately, silicon into iron in its core. At that point, it goes supernova, and it leaves behind either a neutron star or a black hole. And that's it. In a nutshell.